So here's a sketch of the circuit involved in my situation. Now here's where we were coiling the fine wire. It's going to act as a resistor. Of course, the more coils we put around there, the resistance drops and more current can flow through it. Here's a mistake. So here we got the plus and minus of our 150 amp 5 volt power supply. Now when we're trying to charge the system, we'll follow the plus lead to here, and this connects to the bottom side of here, and there's a diode, but that would be not able to travel through the diode. So when we have the power supply activated, its current will not go through that diode. It'll be right here. Now this is connected. I showed it loose because before we put the probe in, you had to manually do that connection here and then do that connection. So the probe is already in, so we'll make those connections. Now here's the probe. It's of course pointing down into the magnet, and this is a symbol for the coil of your 100 kilogram or how many hundreds of pounds coil of metal. That's your big bad coil of 70 henries. And this probe has a plus and minus to the outside. It's got some wires inside, and in two places where the plus and minus can come out to touch the coil. Now of course when the probe is removed, this coil has to keep spinning its current, so there is a small section of superconducting, let me draw that in here, superconducting wire nearby the heater. So what they do is have a small heater. It's quite small. You could power it by a 9-volt battery, little 9-volt transistor battery. And it draws about 60 milliamps because it's about 100 ohms. And 60 milliamps is enough to get this warmed up to leave its superconducting state, this section of wire. So once this leaves its superconducting state, it goes from 0 ohms, and this section then has a resistance of approximately 7 ohms. So that's enough so that the current in here, or current from the outside, can be put in here and added in. Of course, if you're adding current from the outside, and let's say the difference of voltage from here to here is about 1 volt. We were seeing that on our device here, the main coil voltage, which is 0 now, because our magnet has. Okay, we'll talk about that in a minute. We want to try to understand what's going on when I wrap stuff on this coil of wire, see what's trying to go on. Well, as I wrap this, more current would be able to flow from the power supply, so I like to travel through the negatives. Negatives where the electrons flow through the resistance here to the other side, back up, and to the top of that diode. And of course a negative force trying to push electrons through that way, it's not going to happen. This diode is not active, keeps on flowing. It goes to the probe labeled negative because that's simply telling you put your power supply negative there. Travels into the coil. There's your magnet. It's into the huge magnet. That's your huge coil, and back out to the plus. The current is traveling through that wire down this current detector, so that lets us see the current, and then on back to this piece of metal, which is connected then to the finally reaching the plus side of the power supply. So as long as this section here is at 7 ohms, it's non-superconducting, we can provide a voltage across there, and that's going to add more and more current flow through the coil. That's how we're charging your superconductor, as long as this is being heated. Now there's two ways this gets heated. It's initially heated by flipping our main switch, which provides that 9-volt transistor battery type voltage, to the 100 ohm resistor, which then heats that. But later on we can just shut that off because there's another source of heat, and that is when we have 0.7 of volt across that section of wire. Well, that's going to provide voltage to travel through 7 ohms, and it's somewhere maybe around in the order of a tenth of a watt, but that's enough to maintain it in a non-superconducting state. So it's not going to leave its non-superconducting state even though we shut off the external heater source. The only way, now what we did in previous experiments is, if whatever current is flowing through this, if you match it by adjusting the resistance here, by adjusting your resistance here, if you match the current, well, let's say there's 10 amps trying to pour out, and then if you have your power supply so that it can suck out 10 amps, I'll have to think about the theory, but all that I can tell you now is if you match that power supply amperage to the amperage flowing in and out of your coil, the voltage drops to 0 across this section of wire. So now it's no longer being heated, and it will cool down and return to superconducting state. So now the current is flowing within itself, and then the current provided by the power supply is flowing down the probe, and it's flowing through that section of superconducting length. But then again, that brings up a little story, and I'll try to explain it here. Here is our coil of superconducting material. Here is that little piece of wire in question, and let's draw some directions here. Let's say we had put a plus here and a minus here in terms of the power supply. Let's write power supply, and that was then having the electrons flow into the plus and out of the minus. So let's just go draw a line to there to show the wiring, and we'll go ahead and connect it through the probe down into the cold superconductivity. Connect it to the probe, and let's try to get some numbers here. Let's say I've got 10 amps flowing this way. Well, if you, let's say, you had 0 amps, let's say you turned off your power supply, then that 10 amps would go this way, and the 10 amps would go that way. You'd have 10 amps flowing in your circle here with 0 ohms, so it'll pretty much flow forever. Of course, I think there's some deal where it does actually lose a tiny amount every year. Well, now let's then turn on the power supply, and let's say we have an adjustable current power supply. Of course, in our system, our adjustable current was because we could change that resistor, which is a big resistor. It's a 500 watt basically. If I was going to run it at 90 amps at 5 volts, so definitely a lot of heat produced. That's my way of adjusting the current from my power supply. Alright, let's say we start out with 1 amp here, and let's see what happens. How do we reconcile this 1 amp? Well, that 10 amps was going to split so that 1 amp goes this way, and normally you'd have 10 flowing that way, but now one of it went that way, so this has now 9 amps. Alright, let's increase this to 2. Well, that means 2 will leave this way and the other 8 will branch here. So you notice as I'm approaching, let's jump this up, let's make a big jump up to 5. Well, 10 amps flows this way, 5 amps flows this way, that leaves 5 left to go down the little section of wire. Alright, you now have 5 amps flowing that way. And let's make the big jump now. Let's crank our power supply to match this 10. Well, now you have 10 amps flowing that way, and then 10 amps continue on there. How many amps are left to flow through that section? That's right, 0. So we now have no current flowing through that superconducting section, and when we match the current that's in the coil of the superconductor. Well, that's great, because if you have no current through there, it's not going to heat up. Well, it's not, okay. If you have 0 amps flowing through this section, and now you have this external little resistance heater, again, that's your 9-volt pop battery, less than 100 milliamps worth of power, just a wee bit of heat to drive that above your 4 degrees Kelvin to make it non-superconducting. Well, no big deal, it had 0 current through there anyways. But that's now let's say now we're at the point you'd want to heat this section up to become non-superconducting for 2 reasons. If you want to increase the current here or decrease the current here. Well, let's do the job of trying to increase the current. So let's change this now to 11 amps by increasing the amperage of the power supply, reducing its resistance in my resistor. Alright, what would that do? Well, when this is non-superconducting, this section, it's about 7 ohms, and you have 11 amps trying to flow. Well, that's 1 extra amp from here. Now, because of this 70 Henry, that's right, it's got 70 Henries of inductance. Inductance is such that the magnetic field grows when you increase the amperage, so that if I suddenly change this to 11 amps, basically none of that extra amperage will be appearing on here right away. So that means we got 1 amp of current being forced to flow through this section of thermal non-superconducting wire. And to do some Ohm's law stuff, 1 amp, 7 ohms, and since ohms is defined as 7 volts per amp, that means we're going to have a 7-volt change or across there if we did such a thing. Well, that's a pretty drastic situation. 7 volts, well, basically 1 amp across 7 volts is, hey, my friend Amin. Amin wants to be a doc. Well, there's Amin, he's over there. He's a nice guy. I'm just giving a talk. I'm recording it on what I'm doing here. Did you want your face to be on YouTube or not? Okay, no. Alright, so no answer there. So 7 watts. That's why deep in that magnet they have a protective diode, probably going both ways, which limits the voltage drop to, maybe if they put 2 diodes in a row, it limits the voltage drop to about 1.5 volts max. And they must have it in one direction and then also another 2 diodes in the reverse direction. Alright, that's I'll take a break from explaining and get back to you in a minute.